This is a tutorial to calculate, design lake loop, surface water heat pump loops, as they're also called, for the coils. The program that we'll use today is GSHP Calc, and we'll begin by entering this button right here. We'll of course agree to the conditions, and now what we're going to do in this particular program today, or tutorial, is to just use a existing zone data file, which in this case the example will be basically a 100-ton system in both heating and cooling. Now we do have other programs that will show you in the tutorials form, that will show you how to enter the zone data from your buildings. But today we're just going to use one we've already made. Okay. So it comes up in this file here, and it's a single 100-ton zone. It's a big building with 100 tons in it. Okay, we'll open that file, and then it leads us to the first screen, which shows us the design entering water temperatures, in this case of the water with antifreeze in it. And for a surface water heat pump system, what is suggested is that you take this number right here, which is the entering water temperature and cooling, and add about 10 degrees to it. Okay, so we're going to use a lake loop today that's got 50 degrees in the summertime. Well, it's a pretty deep lake, and in the wintertime it's got a temperature of 42 degrees. So what we'll do here, if this is 50, we're going to add 10 degrees to that, so that's excuse me, let's get this 60 degrees. And in heating we'll go down about 7 degrees. You see, you got a range here, 5 to 10 degrees. We'll go down about 7 degrees to get this number in heating at 35 degrees. Okay, so these are the temperatures entering those at the conditions. Go to the next screen, and we're going to load heat pump files. Now these heat pump files have been corrected. Rated capacity is very, very optimistic. It's they suggest that the rated cooling capacity is at 80.6 degrees in cooling and 68 degrees in heating. This program corrects it to 75 in cooling and 70 in heating. It also adds in the fan power, which is not included very much in the ratings. That's why they're so very high and optimistic. Now I'm going to pick a machine here that has a scroll compressor. It's a single speed machine and has a electronically commutated fan motor. Okay, and we'll open that up. So what it's tells us is that it's gone in this product line. The largest machine in here is a 70,000 BTU per hour machine, and so it's picked 20 of those to cover the load. But more likely we're going to be using smaller heat pumps. So what we can do is double click on this zone, and then we'll go down here, and let's put some 4-ton units in that. And so we'll assume that all the units are pretty close to performing like a 4-ton unit, even though they may not be that size. And then we'll select the model here. So it's telling us we need 28 4-ton heat pumps to cover the heating load and the cooling load. Okay. Go to the next screen. We're going to use a surface water loop. Before you do that, you may want to put some information for the printout. So we'll say it's a 100-ton lake loop, and that will show up when you print out this information results. So we'll go to surface water. Now here's where we put the information about the lakes, and this particular lake is 50 degrees, pretty deep, and the winter temperature of the lake is 42. Okay. No, we're gonna, yeah. Okay. Now, so what we'll do here at this point is decide what type of material we want. Of course, we don't want any of these other things. They'll either rust, or they're too expensive, or will leak. So we're going to go with the high density polyethylene, and we'll start out with DR11, SDR11, and the 3/4 inch pipe, and it automatically gives us the dimensions of that material and its thermal conductivity. I always like to use different kinds of materials for the lakes. I'm going to use a muddy river, which is pretty much the same thing as a muddy lake. Where I grew up, there's not too many clear lakes, so I like to use this. And we're also going to use 15% propylene glycol, which is probably plenty of antifreeze for our conditions. Okay. They typically will not allow you to use antifreeze that's alcohol based in lakes, so we'll avoid that. Okay. So there's the information we need, and then we'll go to the other thing that we need to put in here, is that we need to know the number of coils that typically we need. It says we need 1 to 2 coils of a ton. Okay, so 2 coils so what we're going to do here is put in 60. Okay, so we have 60 tons. I mean, it's 100 tons, and we're going to put 60 coils in the lake, and we'll see how that works out. Now, in this situation, what we'll have, this has got 9 coils on it. We'll put 10 in it, and then we'll have 6 circuits. So this would be one of 6 circuits with 10 coils on it in this particular arrangement. Okay. So we'll go to the next screen, and it pops out pretty soon. We're going to get the pump. Okay. Now, based upon that 300 GPM, we put a number in here of 60 foot of head, and that tells us we need a 6.5 brake horsepower, which will lead us to a 7.5 horsepower pump. Okay. Now we can click on this button here, and it will give us the minimum efficiencies for the motors. So I'm thinking that probably this is 7.5, so we could probably kick that up to, we could probably find an 88 or a 90% efficient motor, but it's not going to make that much difference in our coil sizes. Okay, so we got all the information we need. Click on this, and that gives us the first screen output. Okay, so here's our results. We have the total lengths here, and the lengths per coil. So you can see these 60 coils got to be 481 feet. So we probably put a 500 foot coil in there. Here it gives them some temperatures about. This is what we put in. It comes out. It goes in at 60, comes out at 69. Goes in at 35, comes out at 29.1. It's flash there because it's freezing, or it's below what normally when a heat pump shuts off without antifreeze protection or freeze protection. And so this one is pretty good shape. So we should be able to expect the 15% propylene glycol would be plenty of material. Okay. Now some other things we can see. This particular machine is cooling. It's doing great. It's really doing good. 19 EER, and that's the worst case condition at design. It'll get a little better at part load, and that's the EER with just the heat pumps included and the fans. And this is when we include the pump power. Okay. Now you can see the COP is a little bit lower than what you would expect for a ground heat exchanger, a vertical ground heat exchanger, because lake temperatures are going to be a little colder in the winter than the ground temperature in most cases. Okay, so we're in pretty good shape here. Now, what we do have to concern ourselves with in this program doesn't completely do it. We need another program to help us figure out what the head loss is. So we're looking at 300 GPM through 60 coils. So we divide 300 by 60, and we got 5 GPM, and we're going to be pumping 5 GPM through a 500 foot coil. That may have been a little bit much on the head loss. So let's look at some other options. And what we'll do is print this off, and then go to another option, then print it off, and then go back to the program called ePipelator and calculate the head losses to see what's a good combination between coil length and head loss. Okay, so let's go to the next screen. And first thing I want to do is to show you to be very careful. Well, let's do this first. Let's go ahead to the water coil specifications, and let's go to the 1-inch pipe. Okay, so we'll go to 1-inch pipe and go to the next screen, and you can see what happened here. We went to 450 foot of coil, so it's a little bit shorter coil. Okay, but the good news is that we're still well above the Reynolds numbers for laminar flow, which is 2300. So we're in good shape. And now what we have is 500 foot of pipe, of tubing, 1-inch tubing, and we're pumping, still pumping 5 gallons a minute through it. Okay, so let's look at that number and let's make sure, you know, your antifreeze salesman may say, oh, you need 30%. So let's see what you do if we listen to that antifreeze salesman. We'll go in here and we'll change that. We'll say, okay, let's put 30% in there. We'll be real safe. Click on there, and next screen, and we'll come up with calculate coil length. Oops, we went into laminar flow, and we now need 534 foot of coil in heating, because we did go into laminar flow. We're still in turbulent flow or transition flow in cooling, but we don't want to do that. So let's back up. Let's do a couple more things. We don't even want to print this off. Let's go back and get rid of that. Go back to 15% propylene glycol. Now, again, we may be pumping 500 gallons a minute through this 5 GPM through this 500 foot coil. So we may not want to do that. So let's go to 72 coils. Okay. So that would let us have, we could still stick with the 6 circuits, but each circuit here would have 12 coils on it rather than the 10 that we had before. Now, so that would, of course, let us pump. We would do. Let's go back to let's go to the next screen, and we'll see what that does. So now we have still above, well above laminar flow, so we're pretty good shape. But now look what happened here. We dropped down below 400 feet on both of these numbers, so we could go with 400 foot coils and do 12 of them, and we would have a lower head loss, okay, because we're now pumping 300 divided by 72, which is about 4.2 or 4.1 GPM per coil. So that would have quite a bit lower head loss. The coil lengths would be pretty much, we'd have 72 coils at 400 foot rather than 60 coils at 500 foot. Okay, so you may want to print this out too. The other thing that you may be concerned about when you have too many parallel piping loops is you could go into laminar flow, but you could also just have to have a lot more connections the more parallel coils you have. So I think I'd print this off and then go back to the pipelator and see where my head loss was to see if my pump size is sufficient. So I hope this helps, and we'll discontinue this program now, and good luck with your designs.